Hello everyone, I am Aniket Koul and today we'll be discussing the 14th problem from the CP-31 sheet by TLE Eliminators under the 1200 problems. So I'll be moving to the CP-31 sheet and we can see that the 1200 parameter has been checked. We'll be scrolling down to find my 14th problem, mirror grid. Let's begin. So the problem statement is as follows. You are given a square grid with n rows and n columns. Each cell contains either 0 or 1. In an operation, you can select a cell of the grid and flip it, that is from 0 to 1 or 1 to 0. Find the minimum number of operations you need to obtain a square that remains the same when rotated 0 degrees, 90 degrees, 180 degrees, and 270 degrees. Right. So there is an example shown below where we have a 4x4 grid which is initially like this, and we rotate it once 90 degrees and then again 180 degrees and 270 degrees, and you can see it is not the same, but we are required to change the grid so that it becomes same in all the rotations, right? Coming to the input format, the first line of the test file would contain a single digit t denoting the number of test cases, which can range from 1 till 100. Then the first line of each test case would contain a single digit n denoting the dimensions of our matrix. Right. So remember that it's a square matrix, so it will be n cross n, and n can range from 1 to 100. Then the next n lines would contain n characters each, that is the entire matrix, and the ith row and the jth character of that row will represent a I comma j, and that is binary, so it will be either 0 or 1, right? And you need to output for every test case a single integer which denotes the minimum number of operations needed to make the square look the same when rotated 0 degrees, 90 degrees, 180 degrees, and 270 degrees. This is our problem statement. Let's understand it better, right? So we are being given that for every test case we have two things, n and let's say mat. So n is an integer and it denotes the dimension of matrix, right? And mat is the matrix itself, right? This is the n cross n matrix, and remember that the matrix is binary. So ai comma j, where I can range from 1 till n and j will range from 1 till n. A of I comma j would be either 0 or 1, right? So it can be either of those two values only, right? So now they're saying, let's say you have a square matrix. So in this example, let's say a 3 cross 3 matrix, right? And let's say you have A, B, C, D, E, F, G, H, I. So these are variables. We know that it can be either 0 or 1 only. So this is 0 degrees. That means it is not rotated anyhow. Let's rotate it 90 degrees, right? And I will explain to you later in the solution why haven't they mentioned rotation would be clockwise or anti-clockwise, right? And I'll prove it to you that it doesn't even matter if the rotation is clockwise or anti-clockwise. But for our case, for simplicity, let's assume that we're rotating it clockwise, right? So try to imagine if you're rotating this matrix clockwise by 90 degrees, how would it look like? So it would be something like this, and then DEF, and then GHI, right? It will look something like this. And then let's again rotate it by 90 degrees. So the total rotation now is 180 degrees from the beginning. And if we try to draw the matrix now, you can pause the video for some time and try to figure out how would the matrix look like now. So yes, it would look like this: GDA, and then HEB, and then IFC, right? And then for the final rotation, let's write it here. For the final rotation, I would rotate it again by 90 degrees. So the total rotation now would be 270 degrees, right? And this would look something like that. IHG, and then FED, and then CBA. right? So now these are the four rotations. Our problem statement says that we have to change the matrix somehow, that for all these four matrices, they should be the same, right? Now, how can we change the matrix? Quite simple. Take some a of I comma j and just flip it, right? So if it is 0, make it 1, and if it's 1, make it 0. So this is the change you can make, and you'll have to change the matrix in such a way that it remains the same in all the four rotations, and you'll also have to make the minimum number of changes. So keep that in mind. So you'll have to change the minimum amount of indices in the original matrix. So this is our question. Now let's discuss an example case to understand our rotations better. I'll be moving back here, and let's choose this first case where, right, paste it here, and let's remove anything that we don't need. Right. And also let's increase the font size, which is better visible. Great. So in this input, as we know, this is n, and this is our matrix mat, right? So you can pause the video again now here and try to draw all the four rotations and check for yourself that this original matrix will not remain the same after all those rotations, right? So you can check that for yourself. Now you know that it will not remain the same if we don't change anything. So what can we change, right? So let's say this was our matrix, right? And what I do is I change this 0 to a 1. So now it will look something like this. Is this? Yes. This is our new matrix. So let's say I change this. So number of changes that I made was 1, right? I made only one change. Now keeping this matrix as original, let's try to rotate it and see what happens, right? So this is our 0 degrees rotation. Let's rotate it by 90 degrees, and you'll have 0 1 0 and 1 1 1 and 0 1 0. So at least for the 90 degrees rotation, I know that it will remain the same. So let's rotate it once again, and for 180 degrees, right? So this would be 0 1 0 1 1 1 and 0 1 0. So again for the 180 degrees rotation, I saw that remained the same. And finally for the 270 degrees rotation, let's do it again. This is 0 1 0 and this is 1 1 1 and this is 0 1 0. So we saw that for the 270 degrees rotation as well, it remained the same. So yes, I can say this is a valid matrix, and the number of changes that I had to made was 1. And you can see for yourself that if I made 0 changes, it would not satisfy these conditions. So the minimum number of changes that I have to make is 1. So that would be our answer. And we can verify that on the sample output as well, that yes, indeed 1 is our answer. So this is how the problem would flow. Now let's discuss the sample cases, or should I say the expect time complexity, right? So we know that we'll have t test cases where t can range from 1 till 100, and we'll have for each test case a matrix which would be n cross n in dimensions, where n can range from 1 to 100 again. So if we just count the time complexity for taking input of all the matrices, then that would be O of t into n square, right? Because to take the input for one matrix, the time required would be of n square, and we'll have to do that for t matrices. So that would be t of O of t into n square. If we calculate this, this would be equal to O of 100 into O of 100 O of 100 into 100 square. That would be O of 100 cube, and that would be O of, I should not write O of exactly, should write 10 power 6 operations, right? This is 10 power 6 operations, right? And for a fact, we know that on Codeforces in 1 second, we'll be able to run about 10 power 8 elementary operations in a second. So 10 power 6 runs fine, right? But if we try to go a little more deeper, so if we go O of t into n cube, we could see that that would be O of 100 into 100 cube, and that would be around 100 power 4, and that is 10 power 8 operations, right? So yes, 10 power 8 operations can run, but this would be a bit too close for our liking, right? So we don't want our solution to go this close to time limit. So we would be best, or we would be better off if we can limit our time complexity to this, right? O of t into n square. So this would be the expected time complexity for this solution, right? So now let's come to a solution, right? The main logic. Now, the first major observation that we can make is that why does the direction of rotation not matter, right? As I said, I would explain the solution. When we mention a rotated 90 degrees, 180 and 270 degrees, we don't mention the direction, clockwise or anti-clockwise, right? So does the direction matter or does it not matter, right? So for this, let's assume that rotating in clockwise direction is positive angle, right? So let's say 0 degrees, I rotated it clockwise 90 degrees, so it becomes 90 degrees, again clockwise 180, and again clockwise 270. So if clockwise is positive, then anti-clockwise would be negative, right? So if I go negative 90 degrees, that would be minus 270, and this would be how much? Okay, I should not write minus 270 actually, sorry. I should write it as minus 90, because 0 minus 90 is minus 90, and then minus 180, and then minus 270, right? But we know that for any angle, right, we can write that theta equals 360 degrees minus theta, right? So I can say that it would be 0 degrees, 270 degrees, because 360 minus 90 is, sorry, 360 plus theta, right? So I'll write it again so it is better visible. Let's draw this inside a box, that for any angle theta, it is equals to 360 degrees plus theta, right? This would be 270 degrees, this would be 180, and this would be 90. So if you see, only the order is different, right? So only the order is different, but the angles remain the same. Therefore, I say that it does not even matter in which direction you're rotating the matrices. At the end, the 4 matrices that we get would all be the same, right? In different order, but they would be the same. Okay. So now let's come to the second major point, where we'll be discussing as to how actually to rotate the matrix and calculate, right, if it remains the same or not. So the first point, let's say if I write a function which rotates a matrix by 90 degrees, right? So let's say I had a matrix A and I applied the function on it and it became A dash, right? And it got rotated by 90 degrees. If I apply the same function on A dash and make it A double dash, wouldn't it make the total angle of rotation to be 180 degrees? Right? Because I rotated the matrix once by 90 degrees, it's so total rotation is 90 degrees. I rotated again by 90 degrees, so the total rotation now is 180 degrees. Right? Let's apply the function again on A double dash and it becomes A triple dash, and the total rotation now would be 270 degrees. Right? So that means I don't need to write 3 separate functions for 3 different rotations. I can write one simple function and apply it again and again to get all my rotations. Right? Now, let's try to calculate what that function would be. Right? So I just want to calculate the function from 0 to 90. Right? So if I get that 0 to 90 degrees change, I can apply it again and again to get all the changes. Right? So for simplicity, let's take a 4 cross 4 matrix and try to see a pattern here, right? These are two 4 cross 4 matrices and I'm rotating it 90 degrees clockwise, right? Now, moving from this point onwards, I'll be using the zero based indexing notation, right? So it becomes easier for us to implement. Don't get confused there. So let's say if I have this index, right? So what would be the coordinates of this index in zero based indexing? It would be 0, comma 1, right? Now if I ask you where this cell would lie if I rotated this matrix by 90 degrees clockwise, right? Wouldn't this cell lie here, right? And what are the coordinates now? The coordinates are 1, comma 3, right? Again, take any other random cell. Let's take this cell. This cell has the coordinates 2, comma 2, right? And if I rotate the matrix by 90 degrees, where do you think this would lie? It would lie here at 2, comma 1, right? So you can make all those patterns and you will see that if you rotate a matrix by 90 degrees, the change that happens is that for any cell, let's denote by mat. So for any cell mat of I comma j, it would move to the cell mat of j comma n minus 1 minus I. This is the pattern that is followed if you rotate the matrix by 90 degrees clockwise. So any value that was at I comma j would now be present at j comma n minus 1 minus I, right? So this is the function that I was talking about. So if you apply this function once on your matrix, you have essentially rotated it by 90 degrees. So let's again apply this function on the new matrix, right? And let's see what happens. So now it becomes matrix of n minus 1 minus I and n minus 1 minus j, right? Because I'm applying the same function. So if I comma j changes to j comma n minus 1 minus I, then j comma n minus 1 minus I changes to n minus 1 minus I and n minus 1 minus j, right? And let's again apply this function because here 90 degrees, here again 90 degrees, and one last 90 degrees, and this would be mat of n minus 1 minus j and I, right? So if you're feeling a bit confused, you can pause the video for a few minutes and look at it, right? The transformation that happens. So what is basically happening is the y coordinate moves to x coordinate and the y coordinate becomes n minus x minus 1. So that is what is our transformation function. And we are applying it again and again. So on the first transformation, we rotated it by 90 degrees. On the second transformation, we rotated it by 180 degrees. And the third transformation, we rotated the matrix by 270 degrees. That is what is happening here. So essentially our problem reduces to this. All these indices, right, they will contain the same value, right, because we are rotating the matrix. So if the matrix has to remain the same, we need to follow one major thing, and that is I comma j, j comma n minus 1 minus I, n minus 1 minus I and n minus 1 minus j and n minus 1 minus j and I, all of these four cells have to have the same value, right? And if we are able to maintain this for every I comma j, if we are able to maintain this condition for every I comma j in the matrix, then we can say yes, no matter the rotation, we will have the same matrix, right? So I'll repeat this once again. For all these four cells, if the original matrix, so I'm talking about the original matrix, if for the all the four cells, the original matrix contains the same value, then no matter at which angle you rotate, like if you rotate it 90 degrees or 180 or 270, it will remain the same, right? So essentially what you need to do is that for every I comma j, you need to ensure that all these four cells have the same value. And if they don't, you'll have to change some of these four values so they become the equal, right? And how do you ensure that they become equal while maintaining the minimum number of changes? Let's see. Let's say out of these four cells, one was 0, other was 0, this was 1, and this was 0. So it is more beneficial to change this 1 to 0 instead of changing all these zeros to 1, right? So essentially what we are trying to ensure is the element that is in minority, you will flip it, right? So if ones are less, you will flip the ones to 0, and if the zeros are less, you can flip the zeros to 1. And if both of them are equal, then it's your wish. You can either change zeros to ones or ones to zeros, and that is it. and that will solve your problem, right? So that is the entire logic of our solution. And now quickly let's look at our time complexity. So what we are essentially doing is that for every I comma j, I am calculating these four cells, right? And calculating these cells is O of one time, right? We are not iterating over a loop, right? So it is O of one time, and now I'm doing this for every I comma j, and I can go from 1 to n, and j comma j can go to 1 to n. I should not say 1 to n because I discussed everything zero base, so I could say 0 to n minus 1, right? So j also goes from 0 to n minus 1. So what I can essentially say is that I can have n values here, n values here. So basically n square values, and I'll have to do this for every test case, right? Not only for just this case, test case. So O of t into n square, like we discussed. And we said that this is 10 power 6 elementary operations. So we are good to go. There is no issue whatsoever. This is the entire logic. Now let's look at the implementation. So first of all, what we'll do is run a loop for all test cases, and for every test case, we'll take in the input for n, that is the dimension of our matrix, and then we'll take the input of the matrix, right? So taking the input here is basically O of n square operation, right? Now we're maintaining an answer variable which will store our final answer, and then for every index, so for every I comma j, what I'll do is I'll maintain the number of zeros and ones for those four cells, right? So I comma j, j comma n minus 1 minus I, n minus 1 minus I, and n minus 1 minus j, and then n minus 1 minus j and I, right? For all these four cells, I'll calculate how many zeros are there, how many ones are there, right? And then if there are all zeros or all ones, then that means all the four cells are equal, so I don't need to do anything. I'll just simply continue, right? I'll move on to the next index. But if they are not equal, so I'll see which is the minority element. So here C1, that is 1 is a minority element, right? So the number of ones will be added to the answer, and I'll convert everything to 0. If zeros are the minority element, then I'll have to change all the zeros and convert everything to 1. As simple as that. So I'll write it here that ones are in minority, so change all zeros, sorry, all ones to zeros, right? And similarly here, zeros are in minority, so change all zeros to ones. As simple as that. And simply at the end of our loop, output your answer, and that is it. That is the entire solution done. And let's write the time complexity here as we discuss. So the total time complexity comes out to be O of t into n square, right? And the total space complexity comes out to be O of t into n square as well, because what we are doing is essentially storing a matrix of dimensions n cross n for every test case. So that is our solution done. Now for the ending remarks, I would like to say that this problem was majorly based on how could you improvise your implementation, right? There are a lot of ways to implement. So one way of implementing could be that you could make all the four matrices. So you could rotate the matrix and store it in a different matrix and make all those four matrices and then compare, right? So that could be an option. And there are various methods to implement this. But what you want to do is essentially simplify your logic. So your logic should be as simple as possible, and your implementation should be as simple as possible, so that it is faster to implement and there are lesser chances to mess up somewhere, right? So that is the entire reasoning behind adding this problem to the CP-31 sheet, that you need to be able to implement anything that you can think of swiftly and in as less lines of code as possible, right? So I hope you like the solution. Thank you.